The electromagnetic wave equation, that EM wave. What is electromagnetic wave? The EM wave from Maxwell's equation. We have the solution on EM wave in Mach 1. The EM plane wave, polarization, energy and momentum of EM wave in homogeneous wave equations. If there is an electric field, there is also being a magnetic field there. Both are perpendicular to each other. The electromagnetic field will be perpendicular to both. That is the EM wave. Okay? That creates EM wave. Now, the electromagnetic wave from Maxwell's equation. As we know, the second Maxwell equation, take a curl of electric field. The third law, Faraday's law, just del cross E minus dV dt. Take curl on each side. Then change the order of differentiation on the right hand side. Change the order of differentiation on the right hand side. You can get this. That means the curl will go through to the B and dt will be outside. Now, as del cross B, it means the curl of B is equal to mu naught epsilon naught dE dt. Mu naught epsilon naught dE dt in previous equations. Substituting the del cross B, that means the fourth equation, Maxwell's equation, it is the fourth equation, to the equation that we have written before. Del cross C, just put the value here, del cross B, just like this. After putting the value, we get the harmonic equation, the second order differentiation minus mu naught epsilon naught the second order differentiation of it with respect to time, so that is square dt square, 2 times differentiation of E, assuming that mu naught and epsilon naught are constant in time. Using the vector identity, now we go through to the vector identity. We got this using vector identity. That means if it is del cross, that is del cross, we can write it like this. That is a separate equation. It becomes, we get the del out of it, that can be a dot product of this, minus, that is del square, and you will say what is del square and how can you write del square. That is known as Laplacian. That is known as Laplacian. If anybody marks you like that, that is known as Laplacian. Okay. And that is a theorem of vector identity. You can write this as this. That is vector identity. You can write this as this. Now usually you can write the part that becomes previously, go through to that. This is the equation. Just put the value there. Put the value there. This is the value here. And in free space, as you have told before in previous slide, I have told you, in free space there is no electric field, there is no magnetic field, so that will be 0. So this part will be 0. Okay. So if this part will be 0, so this thing will be cut off. That will be equal to this, and after that you can write it. If you just change the side, the left with the wave equation, That is the wave equation. That is the harmonic Laplacian of E minus mu naught epsilon naught, second time order differentiation to E is equal to 0. Now, the electromagnetic wave from Maxwell's equation. Now we are heading towards the electromagnetic wave equation. Similarity, the wave equation for magnetic field is that. It's pretty much similar. That is in electric field, just put the B on E. Magnetic field, same as that. Now we know C, that is the velocity of light or the velocity of an electromagnetic wave, is equal to 1 by root over mu naught epsilon naught. That's a constant value. Okay. The solutions of the wave equations where there is no source charge is present. Where there is no source charge is present, the solution of electric and magnetic field will be that. Okay. They can be plane waves obtained by method of separation of variables. If we apply this method, we can get the wave, the magnetic wave, the electric wave out of it. Now, that is the separation theorem, the Phasor form. That is the Phasor form. It is a sinusoidal wave, as we know. That is the Phasor form, and that is the Phasor form. E is equal to E naught exponential to the power I kr minus omega t, like a sinusoidal form. B is also like that. They are same because of this. From this equation and the method of separation variable, that means it is a solution of partial differential equation. Okay, we get that is a method of calculating getting the solution of a differential equation. There is a differential equation. Okay, after applying this method, we get these two equations like this, a very simplified equation where E naught and B naught are the complex amplitude of electric and magnetic fields related to each other by the relation like this. That is the relationship between these two. Calculate these two equations, we can get this. B naught 1 by C K E naught K cross. K is a propagation vector. How that can come? Okay, as we know, C is equal to 1 by root over mu naught epsilon naught. That's electric field, that is the magnetic field. If you take the calculation from it, you can get this. Take 1 by C, mu naught K, get through the mu naught, get the square out of it. Then after the calculation, you will get this. There is another part that I can say you. That is, as we know, electric field and magnetic field are perpendicular to each other. There are another field that is perpendicular to it too. That is the electromagnetic wave, and the velocity of electromagnetic wave is c. The direction in the direction propagation factor will be the k. Okay, there is an electric field, that is a magnetic field density, like that. So you can write this by vectorical representation.